meeting with Vlad and Irene. And it's been a great pleasure to see the very impressive program, interdisciplinary program that you guys are building on campus here. It's really great. So it's wonderful. I'm going to talk to you about something that sounds in general here, as you can see, but the main topic is going to be the safe global water. I'm going to be showing an international perspective. This is a program that we're trying to build as a spin-off of the National Science Foundation Science and Technology Center. I'm now serving as a director. It's called Water Campus, and we also created, this is primarily focusing on new materials for water quality control. So we have a lot of chemists, biologists, engineers, material scientists working there. And then we enlarged that coalition by creating this Safe Global Water Institute, which only idea was to bring the social sciences that we didn't have. So essentially what we realized all of a sudden, that after 30 years of Water Campus, we have a lot of students graduated with very good science and engineering, with absolutely no impact. Nobody was going to be using our technologies, right? So it's important to understand, the policy aspects and other components. Primarily when we're going to address safe global water all over the world. I'll give you a little bit, and this is a repeat, right? So I said, oh boy, so our first there this morning going and talk a little bit about these numbers. So, but I'm going to repeat them for those of you that were not here. And we have a big challenge in the world, and we can look at the challenge in terms of access to safe drinking water in many different ways. I'm going to use, as Deb did, the UN Millennium Development Goals. And I'd like to talk about two of them. Goal 1, target C, which is not water, but it's actually the target in 25 years period was to halve the proportion of people suffering from hunger. At that time, in 1990, there were roughly 1 billion people in the world that suffer from malnourishment. And that was around 23% of the population in the developing regions. Then another goal is goal 7 that she talked about, is to have the proportion of people without sustainable access to safe drinking water. At the beginning of the counting of this exercise, it was 1.3 billion, 24%. And those lacking basic sanitation, 2.7 billion people, or roughly a little over half of the population of the world in 1990, lacking sanitation. So over the years, we are approaching 2015. So where are we? So goal 1, target 1C, and you'll see in a second why I want to talk about food as well today. So we find that people find that we are within reach because we're getting close to being half of that 20. What we really want to cut is not the number of people, but the portion of people. And even if the population went up, we have found out that we're starting to reach the number. I think that because this was evaluated in 2013, and it's actually for 2010 to 2012, that by 2015, it looks like the trend is saying it's going to happen, that we're going to get there. But it's important to realize that we went from roughly 1 billion to a little bit less than a billion. We have roughly the same number in terms of proportion, is different. Now, goal 7, we have that, as Dave said, the UN will tell you that it looks like we're going to meet it. I'd like to challenge here that we're actually not, that we have, we'll have still more than 10% of the people, 11%, which is clearly less than half of that. So if we just look at these numbers, we say, okay, we're already 5 years ahead of the deadline. We're meeting that goal. Will leave 770 million people without access to water. But notice that the change in word here occurred. That we're using the term safe up here, and now when we do the counting, we mean improve. So if someone built a pipe that is taking water from a river that is making women and children work less, that will be considered as improvement. Nevertheless, if you drink that water, it is unsafe. And I'll talk a little bit more about that. So from that perspective, with that new definition, it looks like we'll meet the target. The one, like they said this morning, we're not going to meet is the target on sanitation. We'll have still 1/3 of the world. It looks like it's not going to improve for what we have now. That will not have access to sanitation. That means 36%, which is not definitely half of a number that we have. So, and as you can see, the numbers are very similar. We're not really improving them. We still have 2.5 billion, roughly, people that will not have sanitation. You know, and these statistics are there for, of those 2.5, 1 billion people practice often defecation. So, and the rest have inadequate sanitation facilities. Now, why am I talking about these targets here? And since I was going to talk to you about water, the reason why we cannot provide safe water, even when we improve access to the water, is because we have lack of sanitation. You have lack of sanitation, you're going to contaminate the environment, and that contamination is going to reach your water sources, and therefore you're not going to be able to do that. And also there is a strong connection between nutrition and water quality. As you know, there are many boundaries there between food and water that you can define, and many of them have been discussed here. But if children, for example, get exposed to contaminated water, even if you have nourishing programs being implemented, they may not work at all. So this is the point I just made, that in addition to those people that we do not have access to improved drinking water, there are hundreds of millions more, probably approaching those without access to sanitation, that drink unsafe water from improved sources. So I like to talk about safe water rather than improved water in my presentation here today. And of course, you're familiar with the statistic about the morbidity and the mortality that takes place impacting primarily children. This is, by the way, these are pictures generally we've been taking in the various projects that we have, and I'll talk a little bit more about that later in East Africa. Now, the most affected are many regions in the world. Sub-Saharan Africa, for sure, perhaps we could point it, that is one of the most affected, as well as Southeast Asia, South Asia, and then a little bit in Latin America. That's where the majority of the people are, from the statistics that we talked about before. But I like to remind you that this is a global problem, and we may have it in a lower magnitude, but we also have it in countries like the United States, everywhere else in the world. For example, our students are working with the Oglala Lakota tribe in Pine Ridge Reservation in South Dakota, and when you look at the statistics that you have there, and when you look where the access to improved water is, the water is not safe, they don't have adequate sanitation. So it's a very small portion of our population that it also occurs here. From the perspective of a little bit more of background, I'd like to talk about water resources a little bit, and that was also addressed this morning. They're becoming more scarce, and the scarcity is occurring worldwide, and you could do it by countries, or you can then look at countries and see where you have water scarcity as you have droughts and so forth. So we have the challenge globally, and we also have the challenge locally in places. Of course, climate change is affecting that. So one thing that is happening, as we have less water, we use it, and we have to reuse it, intentionally or unintentionally, directly or indirectly. And the impact of treated wastewater discharge will have, I'll talk a little bit about that later on in my presentation. And of course, in many parts of the world, the lack of sanitation is going to impact the water quality. So this provides even bigger challenges for us, that we need to have new approaches. And when I mean that, approaches, it's not just the engineering, the science, and the social sciences. I'm trying to understand the situations that we have in the communities that we're going to be doing that. Innovation is what we need to do. Let me start to focus. This is a very broad program, so what I'm going to do is give you some examples of the work in which I've been involved with some of the colleagues at the Water Campus and the Safe Global Water Institute. And I'm going to start to think about the specific contaminants that we worry about. And of course, there is a very wide variety. Pathogens tend to be the ones that worry us the most because they have acute toxicity. People get sick from them immediately or soon after ingesting the water. But there is also chronic toxicity effects. But of course, there could be acute toxicity from chemicals, but in most cases, what we have to worry about is the chronic toxicity of long-term exposure to things like, for example, fluoride. Not just pathogens. If you go to Africa, there are many, many regions and places where water has excessive levels of fluoride, and that starts to do, the children have problems with their teeth, the formation in the bones, and so forth. It's quite dramatic effects and very visual. So we have chemicals, of course, many organics and so forth. Because I'm going to be talking about pathogens today, I will also talk about something that we refer to as disinfection by products. When you put a disinfectant in the water to control your pathogens, we don't have things that, or processes that will actually be just very specific to the pathogen. They react with other things that are in the water, and they produce disinfection byproducts that actually tend to have chlorine toxicity. For example, chlorine reacting with organic matter that you might have present in the water, and we'll talk about that. So you need to worry about those two together. It's not a problem that you just control pathogens, but you actually have to control pathogens, and you have to control disinfection byproducts. And you can see this is a map where outbreaks or waterborne-associated infections in the world. And of course, it's very well characterized in places like Europe and the US. If you go to Africa and you really have the real cases that you have there, the map will disappear behind the thing. We just don't have the information. Now let me start to get a little bit more toward the research front of it. So if we start to think about why haven't we solved this problem? Well, one of the things is that the understanding, how do we actually control pathogens with different technologies that we might have, so these kinetics or mechanisms are not well understood. The complexity of what to react with these disinfectants or disinfection processes is, for example, natural organic matter or the organic materials that you may have from lack of sanitation, and then how do you actually end up producing from whatever disinfection process have disinfection byproducts. And then, what of these disinfection byproducts, chemicals that we produce in water that were not there to start with, what are the toxicity in humans, in animals, in the environment, right? So we know that this is something that is very difficult to understand because we've been studying disinfection at the research level for in excess of 100 years now, and we're still doing so. And the DVP, since we discovered a little over 40 years ago, same thing. So it's just something that is taking us a long time, and it gets to be complex. We have all of these barriers, understanding all of these reactions that occurs between disinfectants and the pathogens, between disinfectants and the background matter, and then the biochemistry, how they interact with our body once we have formed disinfection byproducts. Now the point of my presentation will be, leading from this, that as a result of this complexity, there are communities of researchers that have been focusing on each of these cases. So you have conferences, Gordon Research Conference, you may be familiar with, that focus on disinfection byproducts. And you will not find anyone there that actually work on disinfection. It's interesting because, we form disinfection byproducts because we're disinfecting water. Shouldn't we try to connect these two pieces, right? We're looking at the risk and the impact they have in public health. But actually, we do very little of that. Toxicity is even more complex in the human body. So these are communities that they don't talk to each other a lot. The EPA tries to put all these pieces together when they do risk analysis, but even the regulations that we have is also separated by topics, and they have some contradictions in them if you read them carefully. So all of these will benefit from a higher level of integration. So the focus of the rest of my presentation will be to argue that greater integration of DVP and DVP control business practice will be beneficial, illustrating that the impact of DVP control strategy could have on pathogen inactivation efficiency and vice versa, on DVP control, and then making case of the importance of this, advancing this understanding for the development of sensors. One thing that we do is we tend to say we're going to disinfect water like this, or we're going to provide safe water. When we tell people that we're giving them safe water, we need to have means to show that the water is safe. Many times, actually, the water is not. It's an important thing that connects somewhat to the definition between improved water and safe water that the UN has. We don't have the tools today to demonstrate that water is safe after we have done treatment when we deal with pathogens. So let me just give you a couple of cases without, I'll try to cover, I know that we have a diverse composition of expertise here in the room, so I'll try not to get too heavy into my area and try to explain what we have. But, one thing that we're doing in the United States, because we're forming certain disinfection byproducts that are getting regulated, we call them trihalomethanes, haloacetic acid, so since that the EPA has regulated that we have to meet the regulations, some utilities are being pushed, or they are considering at the switching from the traditional chlorine disinfectant to combined chlorine. And those of you in environmental engineering probably know this well. If you're not familiar with it, I'll be glad to give you more detail later on. Okay? And the only reason why they do it is because they meet the regulation system of having a disinfectant. They don't form the disinfection byproducts that are already regulated, and that's what drives them. So let's see what effect this will have on controlling some pathogens. Before I do that, I'd like to tell you a little bit about disinfection byproducts. So if you go to the World Health Organization, the US EPA, they actually regulate certain group of disinfection byproducts that are produced primarily by free chlorine, because free chlorine is the main disinfectant that we use all over the world. So trihalomethanes, these molecules that you have here, are regulated in the US, also by WHO, and guidelines. And some of the haloacetic acid, these are the ones regulated in the United States. Some of those are also regulated by WHO. And you have some numbers here. I'm not going to go into the detail of how these numbers need to be met and checked with respect to what you have in the water. But the bottom line is that some utilities are not going to be able to meet this regulation. So what are they doing? They're going into a different form of chlorine. They're actually combining, just adding ammonia to the water to combine the chlorine. When you do that, the concentration of these become much lower, and you meet the regs. And those are the only ones that are regulated right now, in addition to a couple of others that don't relate to it. And but what happens if we start to, when you put chlorine with ammonia, you form something that's called monochloramine. If you are waters in Africa where you don't have sanitation with a lot of organic nitrogen and ammonia, you're also going to form organic chloramines. And when you have this species, it's true that you will not form this, but you actually form a broad range of other compounds, many of them nitrogenous. An example is haloacetamides. We have observed this in drinking water in the US, and they're not regulated, so they do it, and we know that those are being formed. So why are we concerned about this? So we're concerned because when we start to look, it took us 40 years, well actually 35 years or so, to come up with the regulations for the trihalomethanes, once the information on toxicity was available. It's going probably to take us very long to figure out if we really need to worry about this nitrogenous compound. But the bottom line is that when we start to do now initial experiments, something like cytotoxicity, genotoxicity, of course, what does it mean in terms of carcinogenicity in society? We still don't know the connection there. But when we compare, for example, the haloacetic acid that I showed you before that are regulated in the US with, for example, haloacetamides that you have right here, both the geno and the cytotoxicity that you have for these nitrogenous compounds this is a log scale here. This is a toxicity index. The absolute number is not important. The importance is the difference between. So it's the relative difference. You can see that we're talking 1 to 2 logs difference in terms of toxicity by these compounds, which are not regulated, so utilities don't need to worry about being formed in them. And in general, what we find is the nitrogenous disinfection byproducts are formed at higher levels when you combine the chlorine, and we find that they have that higher level of toxicity. So in general, compared to compounds that do not have that. And we know the chemistry. One of the key reactions is how it forms. We have a lot of aldehydes in water with the monochloramine. You form something that is called a carbinolamine. Those of you that are chemists, this is a very common textbook type of chemistry. But then these actually start to form nitrile, and this carbinolamine actually react with more monochloramine and form the amide. So, and this is a chemistry that is very stoichiometric, and it's happening in the water. But it's not regulated, so we allow this to happen. One other thing that is important when we think about combined chlorine, and sorry, this is my last chemistry slide, is that when we have free chlorine will take constituents that we tend to have in water at different levels. Bromide and iodide, these are naturally occurring ions. You will transform them into HOBr. The bromide goes to HOBr, the iodide to iodate, non-toxic. So, and this does some disinfection byproducts too, but tends to do the same as free chlorine. So you end up with things like bromoform instead of chloroform. However, when we have monochloramine takes the bromide to bromochloramine, takes the iodide to hypoiodous acid. It's not a strong oxidizing agent, so it doesn't take it to the neutral iodate. And these species start to do disinfection byproducts. Why is it important? It's important because when we look at the relative toxicity of iodinated, brominated, and chlorinated disinfection byproducts, we find that the iodinated significantly more bromo, cyto and genotoxic than the bromo, and you don't even almost see the bar for the chloro there. So chlorinated compounds are not very toxic. On the other hand, bromo are more, and iodo, primarily iodo, are of great concern because of the high level of toxicity that they have associated with it. And these are just homologous compounds that either have one iodine, one bromine, and one chlorine so that we can compare for different family of compounds. In general, the iodinated has much more toxicity than the brominated, which has much more toxicity than the chlorinated. So the switch from free chlorine to combined chlorine is making us form more iodinated disinfectant byproducts because we convert the iodine into HOI. Okay, so I'm going to leave the chemistry there. So what we know is that we form a different range of chemicals that has different toxicity. Are we really supplying safer water? And that's a question that is going to take many years of research to answer. I don't think the EPA is going to take a step on that for a while. So what I'd like to do now is just with that background, the difference between the two disinfectants, I'd like not to go back to the pathogens, which is the original reason of why we put a disinfectant in the water. And what I'm showing for you here is comparing two viruses. So this is inactivation of a double-stranded DNA virus, adenovirus 2, and then this is the single-stranded RNA virus, Coxsackie virus, and we have B5 here. So I chose these two to illustrate how well free chlorine can inactivate viruses. And since I know that many of you probably had not seen this infection curve before, I'll describe a little bit of the figures. What you have in the horizontal axis is something that we call exposure, or CT. So you multiply the concentration of free chlorine by how long the water has been in touch with that free chlorine. That will give you the CT. And in the vertical axis, we have the survival. So if you have a 1 here, then to a 0, meaning 100% survival. If we go to 0.1 here, that means 90% inactivation, or 0.1 survival, 0.01 survival, 99% inactivation, and so on. So we have a log scale there, right? So, and I wanted to show these two because in the past we use free chlorine still as a main disinfectant in the US, but we're moving, some utilities are moving away from it to combine. So we think that free chlorine protects us very well against virus, and it's true. But just to show the point that not all viruses do equal with chlorine, right? So there is a factor of 100 in the resistant adenovirus can be inactivated much more effectively, and it has a pH dependence. If you have a high pH, it goes slower. You have low pH, it goes faster with free chlorine. And the same thing happens with Coxsackie, but there's a factor of 100. It takes 100 times longer with the same concentration to roughly inactivate Coxsackie virus to the same level that we did adenovirus. That's all that this data is telling us. What happens when utilities switch to free chlorine? If you look at the CTs that we have here, you have a milligram per liter in less than a minute. You're going to be in business here. Here, you're probably talking an hour to inactivate, depending on which pH you have, the order of magnitude. The number of zeros start to increase here. So when you use combined chlorine, you're going to find that the inactivation kinetic slows down. Combining the chlorine not only will switch the type of disinfection byproducts that we're going to form, it's actually going to make us a little bit more vulnerable in terms of protecting against viruses in the distribution system. So it's something that we need to keep in mind, that this is something that could be an unintended consequence that we're not thinking about. There is another microorganism, it's an opportunistic bacterium, mycobacteria, Mycobacterium avium being the most resistant, so I will show that data, which surprises us in terms of telling us what free chlorine was being able to do for us. Right? So this is something that we don't have it regulated in the US right now, but it's very present in all distribution systems, and perhaps this data support why is it present in all distribution systems. What you have here is the inactivation with free chlorine. So when you have Mycobacterium avium, you're in Florida, 30 degrees Celsius, you are in a treatment plant where you're applying chlorine with enhanced coagulation where you use a low pH. You can see here that we have the same plot as before, the survival, and then we have the exposure here. For example, for 99.9% inactivation, what we call 3 log, a CT of 60, meaning 1 milligram per liter of chlorine for 60 minutes or 1 hour will inactivate that level. But look at what happened when I take it to the distribution system where we use higher pH in the winter time, not extreme temperature, you go below 5 degrees Celsius in distribution systems. So in which now what we have is that the number of zeros here has increased drastically, right? So what we find is actually the CT required for a 3 log is actually 200,000. That means that at 1 milligram per liter, we need 140 days, which it doesn't happen in any distribution system, right? So what this is telling us that when you put chlorine in water, you're not only, at least in the winter time in distribution system, inactivating or controlling mycobacterium, you're probably selecting mycobacterium because what you're doing is controlling microorganisms that are sensitive to chlorine and you're producing some disinfection byproducts that are actually nutrients. You take the organic matter, transforming into things like acetic acid, oxalate, and so forth, and you're going to actually make mycobacterium very happy. This supports the idea that we have mycobacterium present in distribution systems. This is actually one of the arguments that Europeans use with that. You go to Germany, you go to the Netherlands, they don't use chlorine in the distribution system, and perhaps this is one of the reasons why they don't want to do it. That we're actually preserving there some of the microorganisms and pathogens that we have. Fortunately, it's microorganisms that concern us, but the level of concern is not very high, at least in the United States right now. Now, what happened with combined chlorine? The only reason why I want to present this is that, remember the number of zeros here? When we got to combined chlorine, it's not looking very good, but it's definitely a lot better. Right? There is 2 orders of magnitude lower CTs that are required to inactivate mycobacterium. Right? But what we find actually with mycobacterium is that the inactivation kinetic is very complex. It's not a single line that we have here or there, no matter what concentration you use. It's actually much more complex. It looks like when you use high concentrations, you can go faster. When you use low concentration, you will go slower. And then you have a transition in between. And we have speculated and demonstrated partially that part of what is happening here is the microorganism is able to repair some of the DNA damage that you're doing with the disinfectant at this level. So it's a microorganism, is the microorganism that actually can be inactivated better with combined chlorine than free chlorine among all of those that we get exposed to. So let me just, I'm going to go to another case here, but the opportunity here is that it looks like we don't have a silver bullet. Perhaps that's the point I wanted to make here, that we actually would think about using still free chlorine sequential, as we do in some utilities, followed by combined chlorine, so that we can control pathogens better. There's no silver bullet that will control all of them. And at the same time, control the regulated EVPs, but also the emerging nitrogenous EVP. Because if you use a little bit of free chlorine before they combine, you're going to convert the iodide to iodate, and once you do that, you're not going to form the most toxic disinfection byproduct, which is the iodinated nitrogenous EVPs. So it could be an approach for that. And again, this is integrating the 2 pieces when we think of providing safe water. I'm on sabbatical.